In Core 1 of AS Mathematics, there's an equation of a line that we meet, and I want to use this video clip to show you where that equation comes from. For you to be able to see this, you need to have information about a line to begin with, and what we need is to know two fixed points on that line. The next thing we need is for you to be able to understand how to calculate the gradient of a line segment between points. Really just got to check a few things here. So the line segment is basically the bit of the line that would join the two fixed points that we're given. You'll also need to be able to understand everything about similar triangles, how to identify similar triangles and how their lengths are connected. Right, so let's begin by looking at this gradient of a line segment. Here I've got 2 points, so the fact that they've got these small numbers next to the letters indicates that these are fixed points. So this point here, x1, y1 at one end of the line segment, and x2, y2 is at the other end of the line segment. To find the gradient, I'm going to be interested in knowing how far my line increases in height every time I move across by 1 unit. I'm going to need to know this distance up here and this horizontal distance here. This is how I would go about calculating those distances. So the change in height is the distance from this y2 value, the final height, take away the initial height, which is y1. So this distance here is y2 minus y1. The change in the horizontal position from the first point to the second point will be where I end up, which is x2, take away where I began, which was x1. So this distance is given by x2 take away x1. So to find the gradient, I will be doing this calculation. I want to know the change in the y direction divided by the change in the x direction. What we normally use to indicate this is we normally use the letter m to represent gradient. So m equals y2 minus y1 over x2 minus x1. So just to recap, I did say that to find the equation of a line, or to make sense of my explanation of it, we'd need to know two fixed points. We've looked at them. You need to be comfortable with the idea of another point on the same line that's not fixed. So two fixed points either end and a point in the middle that perhaps could move up and down at any position on that line. And you also need to know about similar triangles, and it's this that I want to check next. This is your similar triangle reminder. Okay, so what I've got here at the moment is I've got a picture. It looks like one triangle that's coloured in strips, but it's actually of two triangles. The blue triangle is lying exactly on top of part of the red triangle which is behind, and I'm hopefully going to try and convince you that these two triangles are similar. Okay, now the way I'm going to do that is I'm going to split them up, and then we'll look at some of the things that they share or have in common. So both of these triangles have right angles. And if you remember, the blue triangle was lying exactly on top of this end of the red triangle. So the blue triangle was somewhere here. So that must mean that this angle here is common to both of those triangles. And then the consequence of that is each of the remaining angles, so clearly on this blue one you can see it there, and on this red one here, those two angles must be the same. The reason they must be the same is that angles in a triangle have to add up to 180. Both of these have got right angles, and they also share the same acute angle here on the left hand side. So it forces it to be the case that this angle at the top here must also be the same for both triangles. Okay, now there are other features of similar triangles which we need to perhaps think about and consider, and it's to do with the ratio of the lengths. So I'm going to just invent some labels perhaps for these different lengths. So I'll call this one A, this one B, and this one can be C, and this one can be D. And what happens here is I know that by comparing these lengths, so B divided by A must give me the same answer if I did D divided by C. And that's because I've proved that they're similar because they have the same angles, and one of them is clearly an enlargement of the other. So the ratio of their sides must be consistent for both triangles. Right, so let's have a look at finding this equation of a line. What I said I needed earlier on was two fixed points. So here's one, x1, y1 at the start of the line, and the other one, x2, y2 at the end of the line segment. Remember, lines carry on forever, and so it actually would extend beyond here. But what I'm interested in is the equation of the line, especially focusing on the part that joins these 2 points. I also said that as well as needing these 2 fixed points, we need to consider another point which is free to move up and down the line. And so this one, you'll notice, hasn't got numbers next to the values, and that's because that could vary. These are fixed. This is the first point and this is the second point. I'm introducing this idea of the triangles again. So you can see this blue triangle here is made by having the start x1, y1, and it has its hypotenuse stretching up along that line up to the variable point xy. Here we have the other triangle. So this triangle is from the same start point, x1, y1, but this time its hypotenuse goes the full length of the line segment to x2, y2. And basically my equation of the line is going to come about as a consequence of investigating the different lengths on these what are similar triangles. You can see the arrangement of the similar triangles again here, and it proves again that they are similar. We've still got the right angles, they share the same point in the corner, the same angle there, so it forces these angles to be the same. I can now do the comparison of lengths of these triangles, and this might give me something interesting. So I've moved the 2 triangles apart, but you can see they're still labelled. This one began at x1, y1, and its hypotenuse stretched up to xy. This red triangle began at the same point, x1, y1, and its hypotenuse stretched up to x2, y2. And what I'm really going to be interested in doing is comparing that vertical distance on the blue one with the horizontal distance on the blue one, and knowing that because they're similar triangles, I should get the same result if I look at the vertical distance on the red one compared to the horizontal distance on the red one. So you should be able to follow this explanation here. I've got 2 sides to an equal sign, and this left hand side is my comparison of lengths on the blue triangle. So the top of here is the change in the height, if you like, from the blue triangle, and this one is the horizontal distance of the blue one. This side of my equation is by looking at the height difference between the top and the bottom of the red triangle, and that's being divided by the comparison between where I end up horizontally and where I began horizontally for that one. And because there's similar triangles, I know that those relationships are accurate. So how do I turn this into the equation of a line? So I've taken that equation that I've got set up, which was the comparison of ratios of lengths on similar triangles. Basically what I would do is I would look at this particular area, the denominator of the left hand side, and I would choose to multiply both sides of my equation by that. You can see now that I've done that multiplication. So x minus x1 was multiplied on both sides, The effect of multiplying the left-hand side by this was that I lost the denominator, and the effect of multiplying the right-hand side by x minus x1 is that I get this bracket over here. Right, so this is beginning to look a bit more like an equation of a line, and this is especially so when we consider that this particular fraction here should remind us of what we found earlier on. This is the calculation for finding the gradient, and this particular equation here, this is really, really important. This is a standard equation of a straight line. I can rearrange this if I want to make something that looks even more like our y equals mx plus c, but there's no need to, and at AS level we don't expect that to happen. This is a really important equation. This is the equation of any straight line that connects the 2 points that we had earlier on. You may also use it in this form, and this clearly shows the fact that we're using both sets of coordinates to calculate this equation. I hope you made sense of that. Feel free to read it over and over again until you can really follow where this equation comes from. But the key thing for AS mathematics is you need to memorize this equation, and you should also memorize this one as it includes the calculation for finding the gradient.